Gravitational torque and center of gravity. An object's center of gravity is the single point that we assume its weight acts from. So on this person right here, their center of gravity might be here at this point. In reality, gravity pulls down on every particle that makes up an object. Like in this picture, you can see that gravity is exerting a force and a torque on every single particle that makes up a gymnast. And each particle experiences a torque due to that force of gravity. But instead of calculating the net torque of every single particle, we're going to combine them into the center of gravity, and the rest of the object will be considered massless. If we were measuring the torque acting on this gymnast right here, we know that torque equals force times radius. So the force would be the force of gravity acting on them from their center of gravity. And the radius would be the distance from here to here, as measured from the point of rotation. This is way easier than measuring every individual particle in the body, because she is made up of many different particles. But in order to do it this way, you'd have to ask, all right, what's the mass of her hands? What's the mass of her chest, of her legs, of her calves, of her feet? And then you would have to measure the radius from each of those places to that center of rotation, and then you'd have to add them all together, which would be a giant pain in the butt. So instead of doing that, physicists have decided to just say, all right, all the force acting on a person is acting right here, concentrated in their center of gravity. And it's as if their hands and their feet and their butt and their chest and their head and everything is all concentrated right here in the middle. We can pretend that the rest of the body has no mass and that all of the particles are here at the center of gravity. Not realistic, but way easier to calculate. An object's center of gravity can shift as their position shifts. So for example, this person here, their center of gravity is in this location. You can see they're leaning forward to counteract the extra weight of the child on their back. For a person holding a bag, their personal center of gravity has shifted to the left because the mass of the bag is making up some of the weight on the left, and it's counteracted by more of their body on the right. Same thing with carrying a load of books. If you're carrying a load of books on the front, you're going to lean back a little to shift your center of gravity so you don't fall. When you lift something with your back, your center of gravity shifts forwards, and your back has to exert a force to maintain balance. You can imagine that a person picking up an object is kind of similar to this rigid beam with a hanging mass. You can imagine that this hanging mass is the object they're trying to pick up, and their back is the rigid beam. So as this mass is applying a force or a torque to the front, there has to be an equal and opposite torque coming through their back. And when that torque is in the back muscles, it can create problems and back pain because the radius in between each of these muscles is really small. So therefore, you have to have a large amount of force for a small radius, as opposed to if you were lifting with your legs have a larger radius. So this is why when you are weightlifting, they tell you to keep the barbell as close to your body as possible so that you don't have your center of gravity shifting and then cause damage to your back. These two pictures show an example of bad form versus good form when weightlifting. You can see that when you have good form, that the back is slightly flat, the head is aligned with the torso, the arms are at a slight angle, the bar is positioned just above the shoelaces, giving a straight up and down. And this means that the torque that's acting forwards due to the weight is counteracted by the torque acting backwards from the rest of the mass of your body, and that by positioning your back in this way, it reduces the forces acting on the spine, whereas a curvature of the spine instead means that you are lifting with your back instead of with your legs, and that could cause damage. This, of course, depends on your height, the length of your legs, the length of your torso, So if you have, for example, long legs and a short torso, your longer legs are going to push the back of your body out more, which means that as you squat, your legs will be shifted forwards more. For example, this Olympic lifter, you can see that their legs are at a very severe angle. Whereas if you have a short legs and long torso, you can see that your center of gravity shifts, that your body will be more upright. Similar to this guy, you can see that his shins are almost vertical. An object that is free to rotate about a pivot will come to rest with a center of gravity below the pivot point. For example, when you're holding onto a ruler, when you allow it to freely rotate, it'll shift so that it's hanging straight down, and the center of gravity will be right here below this pivot point. An object is at equilibrium when the pivot point is located at the center of gravity. So for example, if you have two objects on a teeter-totter, you would have to slide the pivot point or fulcrum back and forth until it's at the center of gravity, and that will be the point where the torque to the left equals the torque to the right, and the object is at rest. So it's one thing to have a system in equilibrium. It's quite another for it to be stable. Some systems are more stable than others. You can increase your stability by lowering your center of gravity or increasing the base of support, for example, by moving your legs apart. In this example, a 95-gram meter stick is balancing here at the 35-centimeter mark. Calculate where the 100-gram weight would need to be placed for this to happen. So this is a meter stick. It's 1 meter long, and the center of gravity of a meter stick is right here in the middle. 95 grams. We can pretend, therefore, that the rest of the meter stick has no mass. It's just like an invisible, like a force field, and that all the mass of the meter stick is concentrated right here in the center. So if the fulcrum is placed right here at 35, this is 0, this is 35, the center of the meter stick is right here at 50. That means that the radius from here to here is equal to 15 centimeters. And we're looking to figure out where we can place a 100-gram weight to balance this out. So what's essentially happening is that the torque of the 100-gram weight is going to equal the torque of the meter stick itself. So we can say the force times radius of the weight has to equal the force times radius of the meter stick, making sure that as we do so that we're converting from grams to kilograms and centimeters to meters. So I got a radius of 0.1425 meters, which is 14.25 centimeters. That means that the distance from here to here is 14.25, and that the position would be at about the 21 centimeter mark on the meter stick if we were looking at the lines on the meter stick itself. So, in summary, this answer of 14.25 makes sense because the mass that we're placing is slightly larger than the mass of the meter stick itself, so therefore its radius should be slightly smaller. It is kind of weird in this problem to imagine that the rest of the meter stick doesn't exist, that anything past the first half of the meter stick is like essentially gone. And that happens once again because we've concentrated the mass of the meter stick here at the point in the center. Here's an example with a cat walking along a plank. The plank is 7 kilograms and has a length of 4 meters. The plank is supported by 2 sawhorses, one here and one here. When the cat reaches the right end, the plank just begins to tip. So what that tells me is that this right here is the point of rotation, or the fulcrum, and that this part is not touching the other sawhorse, and therefore is massless, because the weight of the board is concentrated right here in the center. So if we're looking at this problem, we only have to look from here to here. And the distance of this part of the board is 2 meters, because this part of the board over here is now massless and essentially invisible. So we're looking at a 2-meter board. This part of the board right here is 1.5 meters long, and this part to the center of the board is 0.5 meters long. But the mass of the board is concentrated right here in this spot at the center of the board, and we're looking for the unknown mass of the cat. We're going to say that the torque that the board provides is going to be equal to the torque of the cat. This allows us to solve for the mass of the cat. I got 2.33 kilograms. In this problem, a hungry 700 Newton bear walks out along a beam in an attempt to retrieve some goodies. The beam has a weight of 200 newtons and is 6 meters long. The goodies weigh 80 newtons. When the bear is at 1 meter, find the tension in the wire. If I redraw this without the distracting image of the bear and the goodies, you can see we have a downwards force here, a downwards force here, a downwards force here, an upwards force here. Let me label it. What we're essentially going to say is that the downwards torque of the bear plus the beam plus the goodies has to equal the upwards torque of the wire. So let's fill in the bear at a radius of 1, the beam at a radius of 3, which is half the length of the beam itself, the goodies at a radius of 6, and that has to equal the upwards force of the wire times its radius. So that gives us an upwards force of 296.67 newtons. That's not the force in the wire, though. The force in the wire is acting at an angle, and we have found the upwards force. If we zoom in on this upwards force, it's acting at 60 degrees, as shown in the picture. We can solve for our force tension, 342.5 newtons. Nice work today, guys.